Okay, the next standard locus that's in your syllabus will be what we call the perpendicular bisector. So again, we're going back to the fundamentals again. Z minus A modulus. Z minus A modulus will mean the distance of complex number Z from A. Okay, distance of complex number Z from A must be equal to the distance of complex number Z from B. Okay, the distance of complex number Z from A must be equal to the distance of complex number Z from P. So if you fall back into this understanding, how can I have Z such that it is always equidistant from point A and point B? It must be the perpendicular bisector of the line segment joining AB. Okay, that's how you understand it visually and conceptually. So one example to run you through. So if I have a numerical example like this, what you need to do is adjust it. Okay, adjust it into your so-called standard form. So Z minus away another complex number must be equal to Z minus away another complex number. So I'm going to display this 2. Okay, minus 2 plus 2i and 2 on my Argand diagram. Okay, minus 2 and 2 followed by 2, 0. Where is the complex number that is equidistant from these 2 points? I will generate my complex number. So same thing, you must always adjust it into the standard form, and again you must follow this important rule. Same scaling on the real and imaginary axis. And then what you must always display on your diagram is that you must display the equidistance with a dotted line followed by a 90 degree. Okay, this is how you draw your first perpendicular bisector. Okay, let's try again. This one. Are you able to give me, or rather you need to recognize that this is actually a perpendicular bisector. So same thing, adjust it. Okay, it's going to look like this, is equals to 4 minus 4. So it's the perpendicular bisector of the line segment joining minus 4 and 4i. Okay, it's a perpendicular bisector of the line segment joining minus 4 and 4i. So this is your perpendicular bisector. Take note, I must have the equidistance and the 90 degree. Okay, so the next thing that the question asks for is describe the locus in part 1. So again, what do I mean by description? So you know that it's a perpendicular bisector, just say that it is the perpendicular bisector of the line segment joining minus 2, 2 and 2, 0. This is your description. Okay, so if we are asked to find the intersection with the real axis, okay, how do you actually find the equation of the locus in Cartesian form then? So again, you have to fall back into your secondary school knowledge. How do I find the equation of this straight line? Okay, how do I find the equation of this straight line? I have these 2 points. Okay, I have 90 degree. So theory wise, having these 2 points, I can find the gradient of this line. Okay, and you know the gradient of this line is they are supposed to be 90 degree. So you need to activate this concept. N over 1m is supposed to be equal to minus 1. Okay, the gradient of the first line multiplied by the gradient of the second line is actually equal to minus 1. So you activate this property, you find the gradient of the dotted line. With the gradient of the dotted line, based on your secondary school knowledge, I can find the gradient of my locus. Then you know this is your standard equation of straight line. Y2 minus y1 equals to m x2 minus x1. I know what is the gradient already. The next thing I need to know is a point that passes through the line. Where is the point? It is the midpoint of my minus 2, 2 and 2, 0. So with these 2 ideas, you can actually find for me the equation of my straight line in Cartesian form. Okay, so that would be the first way. The other way by which you can actually do is same old issue or same old trick. Let z be x plus iy. So you may let zx plus iy into the equation, activate the modulus, you can get the equation to be x equals to minus half. Okay, so that is the trick to handle this part of the question.